More than a century ago, John Moses Browning organized a set of mechanical principles into one recoil-operated handgun. The U.S. Army fired 6,000 rounds through it without a single malfunction and adopted it in 1911. Since then, polymer frames, striker-fired actions, and double-stack magazines have rewritten the rules of pistol design. Yet today, more companies manufacture the 1911 than at any point in its history. That isn't nostalgia, it's engineering mastery. Over 100 years of it, still holding ground. The answer reaches from Browning's original architecture to the factory floors building it right now. On February 17, 1910, John Moses Browning filed a patent for a semi-automatic, recoil-operated pistol. Granted as U.S. patent 984,519 on February 14, 1911. This document established a baseline for handgun design. The architecture integrated several mechanical systems into a single, cohesive steel frame. At the core of Browning's layout was a short recoil, lock breech mechanism designed around the .45 ACP cartridge. Unlike simple blowback systems where only a heavy spring holds the breech closed, Browning locked the barrel and slide together during the initial microsecond of ignition. Upon firing, the barrel and slide recoil backward in tandem for a fraction of an inch. A small pivoting link then pulls the rear of the barrel downward, unlocking it from the slide and allowing the slide to continue rearward alone to extract the spent casing. This tilting barrel arrangement allowed for a slim single-stack grip profile by housing the straight-walled magazine directly inside the handle. For user control, Browning engineered two distinct safety mechanisms: a manual thumb lever on the side of the frame and an automatic grip safety on the rear strap that blocks trigger movement unless fully depressed by the hand. This layout balanced mechanical safety with direct, natural alignment. The U.S. Army Ordnance Department acted as the institutional evaluator, subjecting competing designs to rigorous comparative trials between 1907 and 1911. Testing evaluated reliability, accuracy, endurance, and serviceability to find a replacement for the service's .38 caliber revolvers. During the decisive 1910 endurance test, Browning's design fired 6,000 rounds with 0 misfires, while the savage competitor suffered 37 stoppages. In side-by-side accuracy trials at 25 yards, the Colt prototype produced an average group diameter of 1.94 inches, compared to the Savage's 2.84 inches. On March 29, 1911, the military formally adopted the weapon as the automatic pistol, caliber .45 M1911. Standardization followed, utilizing common technical drawings and strict dimensional specifications to establish precise physical relationships between components. This mechanical blueprint ensured parts interchangeability across different production lines. Widespread field use during the First World War revealed areas where the physical interface between soldier and firearm could be improved. Instead of modifying the internal locking mechanism, the military applied targeted ergonomic adjustments. These changes, standardized in May 1926 under the M1911A1 designation, shortened the trigger reach and added an arched mainspring housing to alter the grip angle. Fitters also extended the grip safety spur to prevent the hammer from pinching the shooter's hand, widened the front sight, and simplified the grip checkering. These modifications improved handling for a broader range of hand sizes while leaving the underlying short recoil, tilting barrel architecture completely intact. Because the core mechanical drawings and part relationships remained standardized, industrial factories rapidly scaled up production during the Second World War. Contract manufacturers, including Remington Rand, Ithaca, and Union Switch and Signal, produced nearly 2 million units using these exact, uniform technical specifications. Today, producing a 1911 is an exercise in translating John Browning's original drawings through modern industrial supply chains. Because no single entity owns the design, manufacturers act as interpreters of an open standard. The process starts at the raw material level, where the choice of frame and slide production route depends on production volume, price, and intended use. Premium makers typically begin with forged steel blanks, which align the metal's grain flow to handle high stress. Others select high-pressure investment castings to reduce machining time and material waste, or mill components directly from solid bar stock. Regardless of the starting method, performance depends on precise process control rather than the method's label alone. For barrels, manufacturers start with bars of 1440 chrome moly steel or 416 stainless steel, chosen for their machinability and wear resistance under high pressures. Meanwhile, critical small components like hammers, sears, and safeties require materials matched to their specific wear profiles. These parts often start as high-strength tool steel wire or cold-drawn stock, designed to withstand localized shear forces. Whether sourced domestically or from international industrial specialists, these raw inputs form the structural foundation of the platform, long before any cutter touches the metal. The transition of near-net structural blanks into functional components relies on subtractive manufacturing, where operators once manually guided cutting tools along mechanical templates. Multi-axis computer numerical control mills now execute complex machining operations in single setups. These automated workstations mill the slide rails, openings, pin locations, and other structural geometry to secure precise physical alignment. For the barrel, drilled blanks undergo chambering and rifling. Manufacturers shape the internal geometry either by pulling a carbide button through the bore to displace the steel, or by cold hammer forging, which uses high-pressure hammers to compress the metal over a mandrel. Both techniques produce a work-hardened bore with the lands and grooves needed to stabilize the projectile. Once shaped, these components require thermal processing to alter their mechanical properties. Through a controlled sequence of heating, rapid quenching, and tempering, the steel is structurally modified to balance surface hardness and wear resistance with the toughness needed to absorb cyclic impacts. The process concludes with surface treatments to protect the raw metal. Depending on the intended application, components undergo chemical finishing, such as traditional hot bluing, phosphate coating, or modern nitriding, which diffuses nitrogen into the surface to create an exceptionally hard, corrosion-resistant barrier. At assembly stations, finished frames, slides, barrels, and small components converge to form a complete mechanical system. Operators press pins, position calibrated springs, and slide the reciprocating parts together to verify initial clearances. The barrel bushing must seat securely, permitting smooth lockup, while allowing enough clearance to feed ammunition reliably. Automated function checks immediately follow, testing physical relationships between the slide catch, manual safety, and trigger group. Technicians use precision dial indicators and coordinate measuring machines to verify that critical dimensions remain within strict tolerance bands. Before leaving the factory, the assembled pistol undergoes proof testing. Depending on the manufacturer, these final protocols range from standard overpressure proof loads, followed by magnetic particle inspection, to high-volume endurance runs and accuracy testing at specified distances. This systematic factory verification confirms the physical integrity of the platform before any individual hand fitting is addressed. Standard industrial manufacturing leaves every component with a small, controlled range of variation, known as its tolerance. When individual parts are brought together, they form a dimensional chain. In this platform, the chain links the slide, frame, barrel, and locking surfaces. If multiple components deviate toward the outer limits of their allowed dimensions, even by microscopic fractions, the system encounters tolerance stack-up. This accumulation of tiny differences directly impacts how the parts interface during operation. A slide that is too loose on the frame rails decreases consistency, while a slide that is too tight increases sensitivity to carbon fouling. This relationship dictates the boundary between reliable cycling and mechanical binding. Hand fitting functions as the selective correction of these small, part-to-part variations. A skilled craftsperson tests and adjusts specific contact points to achieve an optimal interface. This selective precision is fundamentally different from cosmetic polishing. While polishing improves appearance, functional fitting ensures that the locking surfaces engage with uniform pressure and align identically during every cycle. Not every surface requires the same degree of tightness. Instead, the fitter focuses on key operational boundaries where metal meets metal under load. Achieving this relationship requires significant labor and inspection, far exceeding the demands of a looser drop-in production fit. The resulting system balances precision, component longevity, and field serviceability. By hand adjusting these critical interfaces, the manufacturer prevents premature wear from uneven contact, creating a unit that operates smoothly without sacrificing the clearances necessary for mechanical reliability. In high-volume manufacturing facilities, the primary engineering objective is absolute repeatability. Production lines utilize rigid fixtures, standardized parts, and repeatable machining programs to maximize throughput. On this scale, parts interchangeability is the defining success metric. Factories implement in-process inspection protocols, utilizing automated measuring systems to verify that components remain within specified dimensional limits throughout the run. This high-volume consistency is a significant engineering achievement, enabling the assembly of reliable pistols without the need for manual adjustment. Conversely, the custom-built approach operates on an entirely different manufacturing philosophy. Rather than optimizing for throughput, the custom workshop allocates extensive individual labor to part selection, precise hand fitting, and exhaustive final checks. A skilled builder hand files, laps, and matches specific components to eliminate even the microscopic clearances that mass production must permit for interchangeability. In this context, cosmetic finishing, such as hand polishing and specialized coatings, remains a distinct labor category, separate from the mechanical fitting required for timing and lockup. These contrasting methods dictate the economics of the contemporary market. The custom approach yields a lower production volume, where every hour of bench time, detailed inspection, and specialized material increases the cost of the finished firearm. This premium pricing directly reflects the scale of production and the intensity of skilled human labor. Ultimately, these two paths do not represent a hierarchy of quality, but rather two distinct engineering philosophies. Mass production relies on process control to deliver reliable firearms to a broad market, while custom building uses individual craftsmanship to optimize the physical relationship between every single component in a single machine. The persistence of the 1911 platform relies on an established industrial infrastructure that extends far beyond any single manufacturer. Decades of continuous production have accumulated a vast reserve of tooling knowledge, standardized supplier relationships, and specialized manufacturing expertise across global supply chains. When the United States military transitioned to the Beretta M9 in 1985, ending the platform's 74-year tenure as the standard issue sidearm, production did not stop. Instead, the established industrial base pivoted to serve a rapidly expanding commercial, sporting, and specialized professional market. This shift was sustained by a highly mature aftermarket and service network. Because the physical blueprints are open and standardized, countless secondary parts suppliers, specialized gunsmiths, and component manufacturers operate globally. This decentralized support ensures that replacement barrels, pins, springs, and triggers remain highly accessible, allowing existing pistols to be rebuilt, restored, or customized indefinitely. Surplus and vintage models undergo constant restoration and refurbishment, reinforcing historical interest and collector demand, while new manufacturing entities utilize these pre-existing parts networks to launch new models with minimal tooling overhead. Civilian demand remains consistent, driven by the design's historical legacy, familiar ergonomics, and distinct handling characteristics. Specialized law enforcement units, competitive sports shooters, and historical collectors sustain a highly varied market, encouraging ongoing corporate investment in contemporary variants, including double-stack high-capacity frames and modernized carry configurations. This self-reinforcing network effect, where widespread ownership drives aftermarket parts availability and abundant parts support lowers the barrier to consumer entry, secures the platform's ongoing viability. The design remains commercially relevant because the infrastructure supporting it is one of the most heavily capitalized and widely distributed in the history of small arms. The mechanical architecture of the 1911 established a baseline that shaped how subsequent generations of handgun designers approached semi-automatic platforms. John Browning's short recoil, locked breech mechanism, with its tilting barrel, became a foundational concept used across numerous 20th century designs, including the Browning High Power and the CZ75. Rather than serving as a direct carbon copy, this architectural layout functioned as a reference point for handling characteristics, setting industry-wide expectations for trigger feel, manual safety placement, and grip ergonomics. The physical feedback of the single-action trigger and the intuitive reach to the frame-mounted controls became standards against which newer designs were measured. The 1911 also influenced how the industry viewed serviceability in construction. The clear separation of the frame, slide, and barrel showed that high-pressure firearms could be maintained and repaired through simple component replacement. Yet, modern handgun design has branched into alternative priorities. The widespread adoption of polymer frames introduces lightweight, flexible materials that contrast with the rigid all-steel construction of the 1911. Contemporary duty requirements prioritize high-capacity double-stack magazines, simplified striker-fired mechanisms without manual external safeties, and modular chassis systems that allow users to swap grip frames. These competing philosophies reveal a persistent division in modern small arms design. While the 1911's legacy continues to define expectations for precision, ergonomic feedback, and mechanical refinement, modern manufacturing often prioritizes cost-effective mass production, extreme capacity, and simplified manual operations. This tension between historical mechanical standards and evolving functional requirements ensures that the 1911 remains both a benchmark of classic engineering and a distinct, specialized branch in a rapidly diversifying family of handguns. Today, this mechanical architecture remains more than a steel relic. It is a living benchmark of industrial precision. As mass production shifts toward synthetic modularity, the pursuit of hand-fitted tolerances preserves a fading philosophy of enduring craftsmanship. The platform is no longer just a tool, but an ongoing masterclass in physical engineering. How do you view its modern role? Let us know in the comments.